Welcome to the first ever NSBE BWSI Build a CubeSat Challenge final event. My name is Rebecca Keenan. I'm the lead instructor for the Build a CubeSat course. Over the past several months, teams of high school students from across the country have been working through a rigorous online course to learn how to design, build, and test their very own satellite prototype. After completing modules on orbital dynamics, the space environment, systems engineering, and satellite development tools, including Python programming, the students accepted the challenge to complete a series of hands-on projects culminating in their final presentations today. Each team began developing their hardware skills by building a flat sat and taking a picture of their team with their Raspberry Pi camera. They used that flat sat to learn about the parts of a satellite through subsystem labs. During their final project, the students applied everything they learned to design their very own prototype CubeSat. Each team submitted a design review video to get feedback from our judges. They have now implemented their design and submitted a video demonstrating their CubeSat's performance, which we'll see some highlights of later today. This program is run as a collaboration between NSBE and MIT's BeaverWorks Summer Institute. It's made possible by the contributions of experts from MIT campus, MIT Lincoln Laboratory, and Woods Hole Oceanographic Institution, as well as all of the mentors and coaches who directly supported students. Here to tell you more about BeaverWorks is Joel Grimm.
Hello, my name is Joel Grimm. I'm here at MIT BeaverWorks, which is a collaboration between MIT and Lincoln Laboratory. I'll come back to collaboration in a minute, but I'd like to tell you why BeaverWorks is important. What is BeaverWorks? BeaverWorks is an idea, and MIT is a place where ideas are fostered, grown, and sometimes even kicked around a little bit to see if they're any good or not. The idea at BeaverWorks, started by our BeaverWorks director, Bob Shin, is a place where more ideas can be grown. So BeaverWorks is a place created by Lincoln Laboratory and MIT out of collaboration for collaboration. As a place, and actually we're located in more than one spot. We're on MIT and have an original space at 300 Technology Square, and now have newer space in Building 31 with the Aero Astro department. But that's the thing about ideas, they tend to spread. These places serve many purposes by design, for collaboration, for classrooms, and prototyping. The idea that we can take real-world projects that we see at Lincoln Laboratory and challenge MIT students to develop new and unique solutions, researching, testing, prototyping, as they learn how to be scientists and engineers is one of the strengths of BeaverWorks. An idea is just an idea until you build it. And the shops are where you can do that, to go from ideas to prototypes. So much is learned in the process of creating and building. And as collaboration is key to innovation, we want the collaboration with scientists and students to inspire great things for them to do more and go farther with their ideas. BeaverWorks inspires students to do great things and lead to more great things, like the BeaverWorks Summer Institute. It's a place like MIT where ideas are encouraged and brought to life. It was started in 2016 in response to a challenge to Dr. Bob Shin to create a program that uses the MIT mindset to collaborate, to work together, to use projects to learn how to do things, and with a focus on computer science and artificial intelligence and technologies, and specifically for high school students, because we saw students coming into college without some of those skills. This is what BWSI is at the core. It's project-based with teamwork, and we have scientists and engineers who are doing active research coming to teach courses in the summer. It's so exciting to see them be able to share their research with students. Our first year started small with 46 students, but we had big plans to move forward on this. We started with the Autonomous Race Car Challenge, which was a college level course for MIT students. Bringing it to high school students and seeing them succeed was amazing to see them learn to program by creating these autonomous cars. Flashing forward to our sixth year in 2021, we were able to pivot to run a virtual program, but we're still growing, still creating new content, and still impacting more students. We are creating satellite programs In other areas, they're able to use our same content. We're adding new content every year and increasing the number of skills that students can learn about in different technology areas. Expanding the impact of BWSI, we've got many ways we're trying to do that. We're creating more courses every year, like I said, but not only are we creating more content for the summer program, but we're also putting that content online to make it available for independent study. In the spring and the fall, we have shorter programs that focus on getting underrepresented groups and younger students involved. And finally, we're developing partner programs like the Build a CubeSat program, partnering with professional organizations that help provide the guidance and the mentoring for student teams to build their own prototypes and learn engineering in the process. Finally, BWSI is transformational, providing opportunities for students to learn, to grow farther than they thought they could, and become more than they are. Thank you.
Thank you, Joel. Like Joel mentioned, the Build a CubeSat Challenge is a partner program. We have partnered with the NSBE Aerospace Special Interest Group to help organize and judge this challenge, as well as provide mentors that work directly with each team and provide regular office hours. We couldn't do it without their support. Here to tell you more about NSBE is Gael Gatera.
Hello, everyone. My name is Gael Gatera, and I am presenting this presentation on the behalf of the Aerospace SIG at NSBE in order to give an overview of our organization and our parent organization. So NSBE is a global organization that got founded in 1974 by the Chicago Six at Purdue University. So we have over 20,000 members worldwide, close to 800 chapters. And so we currently have a strategic plan to graduate 10,000 Black engineers or more by the year 2025. And our mission statement is to increase the number of culturally responsible Black engineers who excel academically, succeed professionally, and positively impact the community. So NSBE operates in basically 3 tiers. So we have NSBE Juniors, which are pre-college initiative, K to 12. And so these are students that are involved either in chapters or members at large through challenges and maybe summer camps in order to know if being an engineer is the right career path for them. And so the second tier, which is the one that has the most chapters and most membership, is the college initiatives. And then we have the professionals, which are people who are early career or even late career, who are involved in the professional chapters in the metroplex that they live in. But also the professional memberships has an advantage in that it has special interest groups, in which the aerospace is one of them, which I'm currently part of and representing for this challenge. So famous NSBE members include astronaut Winston Scott, Janine Uzel, who's our current CEO, and Captain Victor J. Glover, who's also an astronaut. So our CEO, Mrs. Uzel, so she actually got appointed by the White House to be on the board of advisors for historically Black colleges and universities. So the aerospace special interest groups, again, operates under the professionals branch. So we have about 4,000 members or so. And our mission is to equip NSBE members of all generations with tools to support innovating aerospace solutions throughout their lifetime. So we have 4 divisions in the aerospace SIG. We have our technical research division, technical development division, and then aerospace advocacy and the JEDI outreach. And which is the JEDI outreach division is the one that got into an agreement with BWSI to deliver the CubeSat challenge that you all took a part of this year. So for the technical research division and the outreach, so we operate through a technical focus matrix that helps our researchers and people involved to kind of narrow down focus on actually what they want to get out of the aerospace industry and what they want to develop in their professional careers. Space applications, aerospace dynamics, air safety, aerospace design challenges, immersive data in aerospace are the few highlighted here. So there are different tracks of research at the Aerospace SIG. So we have our Vision for Human Spaceflight, our East Africa Spaceport Feasibility Study, Mars Desert Crew Expedition, and the Arusha Cabin Structure. These are all researches that our membership are involved in to increase their skill sets or to particularly get better in specific aspects of the aerospace industry that they may not get a chance to in their full-time jobs or university careers. So our JEDI, JEDI is kind of how we named our outreach division. So JEDI is the acronym for Jumpstart to Engineering, Design, and Invention. So JEDI takes the themes from aerospace science, theories and concepts, component design, fabrication, and research from existing ASIG technical projects and applies them to outreach activities, projects, competitions, such as this BWSI Build a CubeSat Challenge, and events for college and school-age kids. So over the past summer, for example, we had these Tech Talk series sponsored by Colin's Aerospace, where professionals came and talked about specific aspects of what their day-to-day life is at Collins and what the cool kind of technologies they get to work on. So we've also hosted Ken Rufin, who is the president of the National Space Society of North Texas during Uri Night. So we host a lot of tech talks, not only JEDI, in order for our membership to get a bit more insight on several aspects of the aerospace world. So our outreach division has several challenges. For example, this Fire Rocket Challenge. It started this year and is operating in Maryland, Prince George's County, Maryland, by the Fire Rocket NSBE Junior chapter. And so this next fiscal year, it will be available for all to actually the NSBE at large. We piloted that at that specific NSBE Junior chapter last year in order to get an understanding of how we'll be operating countrywide. So also we've started this initiative to teach students PCI chapters about satellite systems with CubeSat projects. So we've had one actually in East Africa where the problem statement was to understand how CubeSats are, how really remote sensing for CubeSat tracks locust infestation in the East African region and the Gulf Coast and the Gulf countries. And we also agreed, created a partnership with BWSI Summer Institute for this Build a CubeSat Challenge that will be completed today on May 15th, that you all got a chance to take a part of. So for any more information, you can reach out to Jackie Long, who is our outreach director, and also myself, Gael Gatera, who is currently the outreach deputy. Thank you for your time.
Thank you, Gael. Thanks in part to the support from NSBE, we were able to give each team and each mentor a hardware kit that included everything they needed to complete the labs and build their very own 1U CubeSat prototype. Although the kits don't include space qualified components, they do include representations of each of the major subsystems that you would see on a flight spacecraft. Here to give you some background on CubeSats is MIT professor Kerri Cahoy.
Hi, I'm Kerri Cahoy. I am an associate professor here at MIT in aeronautics and astronautics. I also direct the Space, Telecommunications, Astronomy and Radiation, or STAR Lab. One of the things we do for research in STAR Lab is we develop new technologies and we fly them to space on CubeSats. I'm very excited to be here and be involved with the BWSI Build a CubeSat program because we need all the help we can get. Developing and building and operating a space mission takes a lot of people in all different disciplines, and I'm excited to be working with you guys and look forward to hopefully seeing you either working with us in our lab or in the industry in partner labs in the near future. I'd like to just show a few slides about CubeSats, their history, and how they get to orbit. On this first slide is an illustration of a mission that we're working on for NASA. It's called the CubeSat LaserCom Infrared Crosslink mission, or CLIC, and we're going to send up 2 CubeSats, CLIC B and CLIC C. There is a CLIC A as well, to do a crosslink of data using lasers from satellite to satellite on orbit. All right, so CubeSats. There used to be a big amount of interest around what would happen when the year changed from 1999 to 2000, and the CubeSats were invented in 1999. The CubeSat unit is called a U. 1 U is 10 centimeters, a cube with 10 centimeters on each side, and the standard mass is about 1.33 kilograms. You can, in theory, stack and combine your CubeSat units, kind of like Legos almost. We are working on that, as I'll show in the next slide. And here's a couple of images that show the scale of a person working on a traditional satellite compared to this little red box here, which is the size of a CubeSat. So that's about the size scale. So satellites, we basically shrunk them and their capabilities from being something that was nearly school bus sized to something that was much more like a shoebox. We are working at MIT in my lab on an idea to stack them together even more like Legos. So this is a project that 2 grad students, Mary Dahl and Esne and Meng, are working on, where we have a robot to put together CubeSats on orbit. And so we had the students develop parts that snap together and can hold an electronics board in each, and you could have a container of different parts on orbit and then be able to put them together on orbit in just the way you needed, with just the right amount of propulsion or the camera or the electronics board you might need, or to replace something. So this is just to emphasize that, we really would like to stack them together like Legos, even if it's not quite like that right now. And this would reduce cost, and the satellites wouldn't need to really be tested, assembled on the ground to survive the rocket shaking, because they'd just be packaged in their boxes. And it would allow us to get things on orbit even faster than we already do. So this object looks a lot like what a jack-in-the-box looked like, but it's not. It's a satellite. So one of the ways that CubeSats, they were able to convince people to let CubeSats get to launch inexpensively is to have them be protected. If you have a big expensive spacecraft on a rocket, you don't really want to put it in danger by having this, cheap, inexpensive student-built satellite on the rocket with you. So they basically decided that, we'll make a little safe box, we'll put the CubeSat in it and then bolt it to the rocket. And that way it'll only come out after the main satellite's gone, when everything's safe. And that ended up working out. So the spring-loaded box is a CubeSat deployer box. You literally load the satellite in it, snap the lid shut, and then bolt it into the rocket, kind of like this. And not joking, you literally bolt it onto the rocket. So this is an example of some of the earliest ones on top of the Bion M1 spacecraft on a Soyuz initially. So this is BSat 2, 3, and Aussie, and one of the very first doves in the back right. So this is a pretty exciting picture, but yeah, you literally do just bolt them to the rocket, and then you have to get them to orbit. So this is after multiple years of launching CubeSats, people started to really do it in earnest. And this was one of the first missions. It's a PSLV that launched from India, where they actually figured out how to get over 100 CubeSats on board the rocket with one big satellite at the same time. And so this is a kind of fun video that shows 88 planet CubeSats as well as several others being deployed, kind of like clowns from a clown car.
From both sides, one after another.
And they're just coming out one after another. And you can see them kind of deploying. Off they go. And if we wait a few more seconds, they deploy the next one, then they open the box, the spring pushes the CubeSat out. And they just kept that up for a whole bunch of minutes to get all 100 of them out. So that's a big deal, and it's kind of where we are now. So that's one way, is just to be directly launched on the rocket. Another way is to have kind of an intermediate trip where you get put on the rocket, but instead of being bolted to it in the deployer, you're packed away as cargo, and you go to the International Space Station, and then the robot arm or an astronaut deploy you. Here are some examples of that. So on the left, this is a cosmonaut that is pitching out a Peruvian CubeSat. I'm just going to advance to where the action is.
Ready to cast it away.
And
for its, science mission.
so he's on an extravehicular activity, an EVA, and had that CubeSat in his pack, and his job is to deploy it. And so kind of like opening day for baseball, perhaps with a little bit more of a gentle throw. That CubeSat is on its way. Another way to do it is to, once you're unpackaged from the Cygnus spacecraft, is to be deployed from the robotic arm. So they actually put the boxes, the deployer boxes, on the robotic arm, and then they command the deploy. This is actually one of our CubeSats being deployed. Videos are all courtesy of NanoRacks. So these are fun. And this is what they look like. The nice part about being launched from the space station is that they have cameras and astronauts with the cameras. And so you can get really nice pictures of the deployment, which otherwise you're kind of stuck with the slightly grainy video from the rocket, like we were showing from the PSLV. So it's always fun when you get the nice images from the space station. And just to wrap up, we've got a couple more coming up next on the launch pad. So these were two that completely different missions that were developed in my lab that ended up being integrated into the same deployer completely by chance at NanoRacks this past March. On March 30th, our students went down there and put these together and integrated these. So this is Click-A. This is a laser communication downlink 3U CubeSat, and this is Beaver Cube 1, which will be taking pictures, thermal images and optical images of the Earth for looking at coastal change and climate change. All right, well, good luck to everyone. I hope you have a wonderful experience, and I'm excited to be part of it. Thanks so much.
Thank you, Kerri. The Build a CubeSat Challenge final project challenges the teams to design, build, and test a CubeSat prototype for a real science mission. This year, we worked with Dr. Colin Ward and Paul Fusil from Woods Hole Oceanographic Institution to look at using CubeSats with an imaging sensor to detect plastics in the ocean. Here to tell you more about the science behind this year's mission is Dr. Colin Ward.
Hello, my name is Colin Ward. I am a scientist at Woods Hole Oceanographic Institution on Cape Cod in Massachusetts. Woods Hole Oceanographic Institution, or WHOI as we call it, is the largest oceanographic research institution in the world. There's over 1,000 employees, and there's also an academic programs office that is linked up with MIT, where we have undergraduate, graduate, and postdoctoral students. We study all phases of Earth and ocean sciences, and overall our mission is to better understand how the ocean works and how it is being perturbed by human forces. My personal research focuses on the fate of organic molecules in the ocean, such as crude oil or microplastics or even naturally derived organic compounds. So for instance, in the microplastics world, I study how sunlight breaks down plastics into different gases, such as carbon dioxide, that is a greenhouse gas, as well as dissolved organic molecules that can be used by microbes as food sources. The science mission for the Build a CubeSat challenge this year is motivated by one of the most pressing environmental issues today, plastic pollution. It's estimated that upwards of 10 million tons of plastics enter the ocean each year, but the fate and ecosystem impacts of this material are poorly understood. When this plastic debris is exposed to the elements, specifically sunlight, it can be degraded into smaller and smarter particles, often called microplastics. These microplastics generally cause more harm than the larger pieces of plastic that they're made from. However, it's extremely challenging to clean up little pieces of plastic in the ocean. So one of the short-term solutions to the ocean plastic pollution problem is to clean up the larger pieces of plastic before they become smaller pieces that can cause ecological harm. One type of plastic that the community is targeting is derelict or abandoned fishing gear, such as nets. Sometimes these nets are referred to as ghost nets because we don't know where they came from or who they belong to. These materials make up nearly half of the floating plastic debris in the oceans by mass and have a huge potential to be broken down by sunlight into microplastics over time. So for example, a net that was 1 cubic meter in size could become 1 billion cubic millimeter microplastic particles as it degrades by sunlight over time. So instead of aimlessly cruising around the ocean looking for abandoned fishing nets, our scientific mission for you all was to develop a small cube satellite that could spot floating fishing gear from space. This information could then be relayed to cleanup crews on ships to remove these fishing nets before they get broken down into microplastics and cause ecological damage. I apologize that I won't be able to attend the final presentations. I have a newborn at home that needs my attending, but I sincerely hope that the missions went well and that you learned a lot thinking about the ways to solve this important environmental problem. Feel free to reach out anytime if you have follow-up questions or would like to learn more about WHOI or Earth and Ocean Sciences in general. My email is cward@WHOI.edu. Have a great summer, folks.
Thank you, Colin. Now it's time to hear how you approached this mission. After each team presents, we'll have a few minutes for questions from our judges, Gael Gatera and Sarah Gomez, and from all of you in the audience. Please post any questions you have for the teams in the box on the webcast page. First up, we have Team LEOnidas.
Hi. Julian, do you want to start?
Yeah, sorry, my mic was muted on my headset as well. So we are Team LEOnidas for the NSBE BWSI Build the CubeSat Challenge. On the left, you have our team member Krigor. Next to him, to the right, is me, Julian. To the right of me is Nari. To the right of her is Peter, who is here. And to the right of him is Declan. Nari and Declan were unfortunately unable to attend today.
So our idea was to differentiate between plastics and the background in the case of the ocean based on color. So the code we wrote would get the Raspberry Pi to take a picture and then write to a text document the location of each pixel that was flagged as being something other than ocean. And then these pixel coordinates can then be used in conjunction with the timestamp and information about the satellite's orbit to find the location on Earth.
While we were testing, we were able to identify sources of our plastic analog that we used on our poster board. In future testing, we want to do several more iterations of code and testing. However, the general concept of our detection method was confirmed as being a good concept, and it worked. Some sources of error were lighting for the camera, which we need to find the best lighting for the camera, and reflection off the poster board surface. So in our further testing iterations, we want to include better default RGB profiles, and we also want to improve our confidence thresholds for pixels of the image flagged.
So for scaling the design to a flight spacecraft, we would want to transmit the information via radio. So that would come with a variety of new challenges, such as noise and so on. There would also be the possibility of image compression, but that may not be desirable due to lost data. On a flight spacecraft, we would definitely want to have a higher resolution camera, as currently 1 pixel would cover several thousand square meters, possibly up to. And then also photos would then be taken at certain times so that it is known what is being photographed on the Earth. And also durability would need to be taken into account for a flight spacecraft, which was not an issue for our tests.
Okay, so as for key takeaways, we found that there were a couple lessons that came out of this, which were imperative to a successful mission. So first, clear communication between teammates, and then also whenever being stuck on a problem, to share it with your teammates and mentors instead of trying to solve it yourself. Also having proper time management, which emphasizes efficiency and productivity, is very important. In addition to that, keeping track of major dates so that everyone's up to date with what milestones need to be reached and at what time. And then finally, asking for everyone's input, as their feedback is always useful.
Thank you very much for listening.
Thank you, Leonidas. We now can take questions from the judges or from the audience. So please go ahead and post your questions in the discussion box on the webcast, or students here on the Zoom, you can post questions in the comments. And I'll open it up to our judges, Sarah and Gael, for their questions. Sarah, do you have a question for the team?
Yeah, I do. All right. Hi, Team LEOnidas. My question is, what do you think was one of your biggest challenge throughout this process?
I think one of the main challenges, I think, was kind of like possibly like kind of like the scale. Like everyone on our team is very new to this. We're like all like sophomores, and this is kind of like our first kind of like, this is our first experience with like these concepts on such a large scale. Like I had some Python experience, like we all had like experience in like general terms of these applications, but it was like it was challenging to kind of like apply them to such a like large project.
All right, thank you.
Thank you, Leonidas, and congratulations on completing the Build a CubeSat challenge. On deck, we have Astra Navis, but right now we have Evanston with a pre-recorded presentation.
Hello, we are the ETHS Spacer Bus Wildkit CubeSat team. I'm Rohil Bose, and I'm a junior.
I'm Maris Goldfarb, and I'm also a junior.
I'm Connor McGuire, and I'm a senior.
I'm Lucas Zerga, and I'm also a junior.
And this is our final project.
So our first thing is the table of contents. We have our system overview, which is what we want to achieve with the mission and what we need from our design to accomplish the goals. We have our demo results, our video of the simulation and how it relates to a possible deployed CubeSat. And finally, we have our takeaways, what the demo told us about the work we've done and our progress so far.
So now let's look at the system overview. So our CubeSat system consists of 5 separate subsystems: the attitude determination control system, the structure system, the power system, the imaging system, and the communication system. First, we're going to look at the attitude determination and control subsystem. So this consists of the IMU and the Raspberry Pi, and they send values back and forth to each other. So let's look at the challenges that we had. So the goals of this subsystem are: we want to obtain quick and accurate roll, pitch, and yaw values to take photos, and we want to use the accelerometer and magnetometer to get RQY. So Some of the issues that we had with this were that the roll and pitch values were accurate after calibration, the yaw values were not, and we had errors from the legacy code from the FlatSat challenge. Next, let's look at the imaging subsystem. This consists of only the camera, and let's talk about the challenges from here. So the goals are to create an algorithm that can identify small plastics on the ocean, and we want to use minimal runtime and resources. So to do this, we chose the color distance algorithm as the easiest to accurately calibrate off of the test images. It also uses less as resources as it just counts pixels, not identifies their location in clusters. And once the abnormalities pass a certain threshold, then it will identify it as plastic and save the image to a to downlink folder. If not, the image will be deleted to save resources and not downlink unnecessary information. Some of the issues that we had with this were errors with the camera reset time, and which sort of offsetted some of our gains, and small plastics are sometimes passed off as noise based on our calibration.
Next, we have the communication subsystem, which is in dark red, and it consists of the Bluetooth connection between the Raspberry Pi and the ground station. So the primary goal of the communication subsystem is to be able to downlink images and receive commands from the ground station. In terms of challenges, communication was particularly difficult because our school because of the lack of a reliable ground station. Available machines either didn't have Bluetooth or had their Bluetooth severely restricted as per our school code.
And as the final subsystem, we will be talking about the structural subsystem. This includes all the parts that carry a physical load and physically connect all the objects together. So the goal of the structure subsystem is to support all the other subsystems in their actions. So for the extent of the mission, we want to make sure that it doesn't impede or prevent or completely take out any of the other systems, because that would that would make the entire FlatSat or the entire CubeSat not work as desired. To create this structure, first modeled the structure in CAD using provided materials, and then once we assembled a structure in CAD, we were able to assemble a physical model. We came up with a number of issues while assembling. First and foremost, the holes on the aluminum L brackets did not line up with the holes that were laser cut on the acrylic pieces. So this led to us having to only attach a few of them and using glue for the rest of it. Additionally, the acrylic is very brittle to the point where if you slightly over tighten a screw, then it will shatter the entire piece and you need to use either a new piece or glue to hold it together. Finally, we noticed that the Raspberry Pi was getting quite hot in our normal atmosphere, where it can both conduct, convect, and radiate away heat. And it was thermal throttling slightly. So in the vacuum of space where it cannot do any of these except radiate away heat, we would expect this to be a much bigger issue.
So now let's get into our demo results from test day. So as you can see, we have 4 photos that we have. So first we have the no plastic photo, which is just a blank photo as the ocean with no plastic on it, and that correctly identified as having no plastic. The plastic, there's a large plastic photo and a small plastic photo that also correctly identified as having plastic. And then there was a tiny plastic photo, which was about 1/5 of the size of the small plastic photo you see above, and it actually incorrectly identified it as having no plastic. The reason you can't see those 2 photos is because they were deleted as a result of our algorithm not identifying plastic. Now let's look at the test day errors. So the yaw values of from our RMU were highly erratic. So to compensate for this, we have to increase the RPY deviation threshold to compensate. And we were also unable to downlink to a device via Bluetooth as mentioned above. So the sources of these errors were bad magnetometer calibration, and we were also unable to downlink to a device via Bluetooth as mentioned above.
And now we'll talk about how we would scale the prototype to a full satellite. So first we would want to improve the mission length by improving the structure. So we would want better manufactured acrylic panels and L brackets so that they would fit together and they wouldn't be as brittle. We would also want to improve the solar panel, as our current solar panel does not provide enough power to charge the battery, and then the battery itself does not have that long of a battery life, so the Raspberry Pi dies rather quickly. We'd also want to improve the mission capabilities of our satellite by improving the IMU and making it more accurate so that we are able to position our satellite more accurately. We want a camera that would be higher quality, so we'd be able to take better quality images of the ocean and be able to identify plastics at a much better. And we would also want to improve the communication system so that we can actually communicate with the satellite from Earth all the way into space. We'd also want to consider a propulsion system for a satellite, because we don't want our satellite vulnerable to any obstacles that it might face in space. And then we also would want to consider a cooling system for the Raspberry Pi, because in space we're only able to radiate heat, and we're worried that our CubeSat would potentially overheat.
This leads us into our takeaways from this project. So starting off with the lessons learned, the biggest was record observations early, often, and multiple times. We had a number of times where an error would pop up and we wouldn't know when this error popped up, so we don't know what subsystem or what component we should be looking at for the cause of this error. Additionally, for an event like this, where we are trying to document our progress and show this to other people, it made that step more difficult on the last day, where we were trying to conglomerate all of different information, because there wasn't that much to conglomerate. We had to really look for what we had. Additionally, we knew that there would be errors, but we didn't consider correctly how often and how large errors would be when we were doing everything. This threw us off with the amount of time we were budgeting for things, so didn't work well. We would then move on to what we would do differently for the next time. And so for the documenting things, using things such as our phones to videotape when we're assembling a structure, or continuously saving the code in a way that we can look back at our past history, such as are available in a number of the coding IDEs. This makes it easy so we know what we have and we can share it with those on our team if they have to miss a week, or with other people who we are doing the project for. Also, doing component level and subsystem level testing before we conglomerate all of the systems into one thing, ensure that even though it would take longer at each step, overall we wouldn't have this integration difficulties at the last step. For watching. In this video, we have gone over the system overview, the demo results, the scaling, and takeaways. From the ETHS Space Bus Wildkits, thank you for watching.
I think we lost Rebecca's camera. Sarah, do you want to jump in with questions maybe?
Sure. I know you mentioned just testing and errors that happen. Is there something else that you didn't expect throughout this process, looking back?
I think I'll take this one. So the timing of this project, I think we focused, we had basically procrastinated a little bit at the beginning, which is when we had the most time, because at the end, we were sort of swamped with like AP exams and the SAT. So I think we all agreed that we probably should have spent a lot more time working on it at the beginning instead of having to cram along with like all these tests at the end. So that was one of the things that was an issue.
Yeah, that's an important lesson for sure. I think for projects like this, you always want to have ample time for testing. And that's a great lesson to take for future projects if you all decide to become engineers. So that's awesome.
Thank you again, Evanston. On deck, we have TurtleBox. Up next is Astra Navis.
Okay. Hello, everyone. We are Astra Navis from Brooklyn Technical High School, and we present to you our work for the Build a CubeSat Challenge. My name is Nora Shams, and I'll be presenting today with Haojing, Sam Huang, and John Lee.
Hi, everyone.
And a quick overview of what we will be showcasing today in our presentation. And to ConOps we go.
Our concept of operations, before launching our CubeSat into space, we will perform tests on each of its subsystems and making sure that they all work accordingly. Once it is launched and deployed in the lower Earth orbit, the CubeSat will map its location and start taking photos at fixed intervals and compiling and sending the data to the ground station during specific parts of its orbit. Back on Earth, the ground station will receive and compress the data and process the data via image processing and storing them into a database. And for this is our system block diagram, which shows an overview of each subsystem within our CubeSat and how each component connects to each other. For the command and data handling subsystem, we have the Raspberry Pi 4, which is connected to most of the other subsystems. For the structure subsystem, we have the acrylics and aluminum chassis and deployable solar panels. For the power subsystem, we have a solar panel, a power distribution box, and a battery. For attitude determination and control system, we have the Adafruit 9 degree of freedom IMU chip. And then we have the Pi camera for optics, Bluetooth for communication, and a laptop as our ground station. We also made a CAD model for our CubeSat using Autodesk Inventor. We imported some 3D models from GraphCAD, such as the Raspberry Pi, the IMU chip, solar panel, screws, and the camera. But we also made many of these components ourselves, such as the case for the camera, the acrylics, aluminum railings, standoffs, L brackets, and the battery using Autodesk Inventor. And then we assembled everything together in an assembly in Inventor as well.
Hi, so this is our bill of materials. We have 19 unique items that are needed to build this CubeSat. For this acrylic for the acrylic panels and aluminum railings, those will need to be bought and cut to the appropriate size, as they're bought in a much larger size than we intended. And extra attention will be needed for the drilling of the aluminum railings and acrylic panels for the hulls. After finding the unit cost of each item and their quantity, the estimated total cost of the whole CubeSat is $210.07 from what we estimated. This is our mass budget. Regarding margins, generally it's used for unseen addition of weights to a specific component. However, with our CubeSat, we don't really have that problem, as nothing new would be added. So in our case, our margin is there to measure the potential weight difference from what is measured / estimated. From some of the measurements were taken off of Autodesk Inventor using iProperty, while others were using equipment that we had available to us. From the total mass of the CubeSat will be estimated about 444 grams, but with a margin added, it would be about 484 grams. And this is our power budget for our CubeSat. They were estimated using various different sources. And our CubeSat has 4 subsystems that were previously mentioned, with 2 modes now, with active and inactive. So with data command and data handling, the Raspberry Pi will consume about 5.5 watts of power with contingency about 20. Various sources that it can use up to 6 watts. So we weren't sure. And then for our EPS, which is our battery, is estimated to use 10.5 watts of power. And the contingency is relatively low since it was based off what the manufacturer was given to us. Our ADCS, or Attitude Determination Control Subsystem, is an Adafruit IMU. From the manufacturer, they also say it will use up to 0.6 watts of power. For our payload, which is the camera, is estimated to use 1.16 watts of power, but there are various sources and the estimates were various, so resulting in a high contingency. And for our CubeSat, we have an active and inactive mode. Our active mode is with all the subsystems on, and that will use about 19.61 watts of power, while inactive is basically a camera turned off for allowing download images to the ground station, and this requires less power, which is about 18 watts. Our next slide is presented by Chris. Unfortunately, he was not able to attend today. However, he did record an audio audio file was.
I think you forgot to share audio.
The audio is not playing.
Here's our software architecture. Once started, we will set a variable named threshold to 0.01. We will then start reading the acceleration of the x, y, and z using the sensor given. If any of the accelerations is greater than the threshold, then we will tell the CubeSat to take a photo. If not, then we will start reading again. We will then start reading the magnitude of x, y, and z and calculate yaw using the formula given. If yaw is pointing north by checking if yaw is greater than 0 and less than 30, then we would then begin to start pushing the photos taken to GitHub. If not, we will go back to reading. Once we finish pushing to GitHub, the program will start looping again until we decide to end the program.
On to link budget. First, let's look at our link budget in orbit with our current specifications for the CubeSat. Skimming over the givens, power from transmitter and satellite are 38 and 3.1 watts respectively, and some additional givens. Going through the budget, we can see that effective isotopic radiated power, EIRP, free space path loss, FSL, power received, noise, and signal to noise ratio, SNR, both for transmitter and receiver. With a negative SNR, it is hard to pick up signals, if not impossible. Looking at the Shannon channel capacity limit, the transmitter is able to transmit to the satellite with a reasonable limit. However, the CubeSat has an undefined value due to the SNR being negative. However, implementing a radio to conceptualize a real mission, we can achieve a better result. A UHF VHF radio with a frequency of 438 megahertz and higher operational temperatures of 358.15 Kelvin. With this radio, we can achieve a positive SNR value about 8. This also gives us a workable Shannon channel capacity limit of about 11. Looking at the change of the limit versus the radius from the ground station, the limit does not change very much, allowing a constant limit. For uplink, we can assume that it will be similar and will actually have a higher limit for the rate. Now, we should look at the data budget to analyze data to find if it is feasible. First, we need to specify the specifications. The camera will be using a 8-bit depth and a max resolution of 3280 by 2464 pixel. It produces about 8 megabytes of data per JPEG file. With a theoretical limit of 11.8405 megabytes per second using the UHF/VHF radio, the downlink frequency of the image transmission is 1.4651 hertz or images per second. At an orbit of 160 kilometers, the speed of the CubeSat should spend about 1,596 seconds connected to the ground station, meaning the ground station can receive about 2.17 gigabytes of data from the CubeSat. Assuming an idealized orbit over the Pacific Ocean and considering the FOV of the camera from our tech demo that showed a view of 193 kilometers by 145 kilometers, the CubeSat should be taking images every 24.587 seconds for a total of 65 images. That equals about 525.32 megabytes of data. Out of the total 2.17 gigabytes of possible data that can be transferred, 525 megabytes is a meager value. This means more images can be taken for precision, even leaving plenty of space for telemetric data from the IMU and other sensors that we could potentially implement for a real mission.
Here's a picture of our CubeSat and tech demo. For our CubeSat prototype, we couldn't get the Bluetooth communication to work and ended up using Wi-Fi to upload the images to GitHub. The images were successfully uploaded, but they had a red tint that we couldn't get rid of. Our CubeSat was able to locate its position in its orbit using the magnetometer in the IMU chip. And we were also able to make it take pictures in particular sections of its orbit and upload the images in the other, also using the magnetometer. Finally, we were not able to use the solar panel to charge the battery, as it was only able to generate approximately 2.7 volts to 3.7 volts, whereas we needed at least 5 volts to charge the battery.
To scale our mission to a real mission, we need to make some changes. Starting with materials and structures, rather than using acrylic, we would switch to aluminum for a lightweight and coating safe material. Less mechanical fastenings to decrease the part count and will also create less points of failure. A lighter power source, a larger solar panel for better charging, and radiators for cooling. For communications, radio over Wi-Fi. Implementing our previously mentioned UHF/VHF radio. For our budgets, for our link budgets and data budgets, we would also need to account for additional disturbances. Operation and mission. Include a calibration phase using images and the IMU working together. And to keep accurate position measurements, a GPS tracking system would be better. For maintenance, for a real mission, we would need to account for course deviation and orientation changes.
For reflection and lesson learned, we should delegate tasks more effectively based on each member's strength and weakness. Like, for example, some of us were stronger in coding, while some others were stronger in CADing. Communicate more effectively and efficiently within the team. Allocate more time for testing, since not everything works in theory or work physically. And more effective use of resources, such as Piazza, mentors, and special office hours. Thank you, everyone, for listening to the Astra Navis CubeSat presentation. We will now open the floor to any questions.
Thank you, Astra Navis, and congratulations on completing the Build a CubeSat challenge. I will once again open it up to the judges and the audience for questions.
Hello. So which aspect of the development of your CubeSat was the most time consuming, and how would you mitigate that if you were to start over?
I thought the physical assembly was the most time consuming, at least for our prototype. I think as other teams previously mentioned, the parts were not correctly manufactured, and we had to drill our own holes. So we drilled our own holes in the aluminum chassis in order to screw in the acrylics, and many other instances, such as the we also had to drill holes on the flat sat, so the wire, so we can actually wire the Raspberry Pi when it's assembled as a cube. So I say assembling the physical CubeSat took the longest due to manufacturing errors. And yeah.
I have another question for Astra Navis team. Great job in presentation. I did notice that the software architecture, it talked about how you push images based on just the position of the satellite. So does that mean that you analyze the images once they get to the ground station, or where does the detection of the ocean plastic come in place?
That we didn't implement a code for that because we couldn't get it to work. We were trying to focus more on like getting it to push using the GitHub. So there were elements that we didn't get to because of time constraints and with APs and other stuff.
But one thing I would like to add for the images, basing off of like ocean current drifts and the like big garbage patches that are in the Pacific Ocean, by having pictures taken at specifically measured, not specifically measured locations, but at time intervals and position measurements. If we are nearing known locations of big garbage patches and taking pictures surrounding those areas, we can pick up other plastics that are also just floating by or have separated and could be lost like into the ocean and not be found later on.
All right, awesome.
Is Rebecca frozen again?
Yeah.
Sarah, would you like to introduce Team TurtleBox?
Oh, I would love to. All right. Yeah. So Team TurtleBox, you're up. Please go ahead and present. I had the pleasure of actually mentoring Team TurtleBox, so I'm excited to see the presentation today.
Okay, I'll start us off. Hello, we are Team TurtleBox, and this is our final presentation. My name is Joseph Lee, and going from left to right from the picture, it's Hee-Sung Yang, Chunhyuk Park, Taeyong Chun, and Jonathan Lee. As mentioned before, Sarah Gomez is our mentor, and our coach is Myung Chun. We are from Torrance, California, which is located southwest of LA, and our members are passionate about not only STEM, but also giving back to our community by teaching what we learned to underprivileged young students in the greater area of Los Angeles.
I'll first talk about our system. Our system contains two parts, the CubeSat and the ground station. When the user runs the code, the CubeSat and the ground station connects directly to each other through Wi-Fi. After they get connected, the window appears on the ground station, and the ground station sends command to CubeSat based on user's input. And the CubeSat runs whatever function the ground station commanded to. It takes picture, detect object by its color or by edges, or running these processes automatically. After running all of these functions, the CubeSat sends data back to the ground station, and the results appear on the window. Here's a demo clip from our tech demo video.
I will first demonstrate the manual mode. So first, I will run the server code from the ground station, which is the server, and I will also run the client code from the CubeSat. After they connect to each other, the window will show up in the ground station that shows the auto and manual mode. As you click Take Picture button, the CubeSat will take the picture and send it to the ground station. After receiving the file, the taken photo will show up in the window. I'll click on the color detection button next. As I click on the color detection button, the CubeSat will detect the plastic by color and send it to the ground station. This detected photo will also show up in the window. Lastly, as I click on the object detection button, the CubeSat will detect the plastic by its edge and also send it to the ground station, which will eventually show up in the window. I'll now demonstrate the auto mode. When I hit run button of the auto mode, it basically runs all the functions, takes pictures, color detection, object detection, and shows all these pictures in the window. When I close the code for the server, the CubeSat prints that connection closed, and it disconnects from the server.
I'll talk about our test and demo results. So the ground station receives the original color detected and object detected images from the CubeSat. And for color detection, we used to set the range of BGR values of the color to leave only the colors in the range and throw out any other colors so that it could only extrude the color we want. And for object detection, it compares the brightness value of each pixel with surrounding pixels and finds pixels that have larger brightness difference than the given set value. It also sends the latitude and longitude of the plastic position so that workers on Earth can go to a specific position and clean the plastics in the ocean. As it had been shown in the tech demo video, many kinds of plastic can be found by both color and object detection, so there will be way less misfinding of plastics. And there was an error that the CubeSat doesn't receive messages from the ground station. The error occurred when the CubeSat is doing work and not waiting for receiving any signals from the ground station, and the ground station sends a signal to the CubeSat and the order does not execute. So it was a code mistake and we could fix it successfully.
I'll talk about how to optimize for a flight. Some changes we would like to make to our prototype to scale it to a flight system is have a bigger and better camera so the satellite can take pictures of the ocean from space in better quality because it would be hard to detect the objects with the current camera. The current camera has lens that was built to use for short distance. So you would need to use telescope lenses in order to take clear pictures from far away. We would need a bigger solar panel to be able to charge the satellite so it can function and work. The bigger solar panel would capture more energy, which would power our satellite. We would need a bigger battery to store more energy and use it as a backup when the solar panel can't collect more energy from the sunlight due to where the sun is and where the satellite is. We also need bigger batteries because it needs to withstand thousands of charge and discharge cycles over the satellite's intended life. Wi-Fi has very limited range to communicate, so we can't connect to the satellite in this space. We would need a big antenna in order to send RF data stronger. Also, we would need another special protocol for sending data between long distance. And the bigger antenna would pick up more signals and send signals to further distances. We would need a stronger material for the structure of the satellite because there are immense hold on objects in space. There are also tons of projectiles that are in space which could damage the satellite. We need strong materials to withstand these obstacles in space so the satellite could be fine in these situations. If we have a weaker material satellite, the satellite would not last in space and probably be damaged or destroyed easily.
Lessons learned. We learned about time management. Some projects we had to do we did last minute, like a week or a day before the due date, which gave us not enough time to check the work we have done. We are very rushed at times. We also learned about double checking our requirements. We double checked Bluetooth link, which was required for communication between the ground station and satellite. We also double checked sending images used by Wi-Fi. Another lesson was code simplification. We got rid of some unnecessary lines of code. For example, sleeping lines. There was no need of them since it will be only on when we turn it on. We also learned about loss of information. When sending image information, some information was lost, so parts of the bottom of the picture were left blank. Reasons for the problem was that the ground station was not ready when the satellite was sending the image. An important lesson we learned was teamwork. We all have our different parts, and we learned how to work with one another to create this project together. The last lesson we learned was step-by-step process. Outside of this project, we would work on things that would only require part of what we did in this project. This project gave us an opportunity to learn and go through the entire process, starting from the design to the final testing and building, which was very fruitful. This was Team TurtleBox, and thank you for listening.
Hello, yeah, I have a quick question. So first of all, great job, especially creating that graphical user interface. So in the real space flight, how would you change, for example, like the auto mode, the algorithm in the auto mode, especially, or the manual mode to detect the specific color values that you want? Let's say you want a specific, take pictures of specific colors of plastics.
I think you can just set the estimate value for each color, like BGR value of each color. Let's say we want to take a video, like we want to identify the color of red. You can just like add BGR value of like estimate like 0 and 255, so that like it can detect by estimate value. Then for finding its edges, I think we should use better camera to like detect it. But then we need to fix some code so that using like another method to finding its edges, because we're just only comparing its brightness value for finding its edges. We need to do multiple like process to like ensure we have found the plastic edges.
Great job. Yeah, I mean, basically there is, you just have to account for changing some of those things in real time instead of having like a specific GUI for a specific, for that one time or for the prototype testing. But yeah, so that's it.
Hey team, great job. Just one question for you guys. So you have more time. I would like to know how you like to improve upon your satellite? Is there something that you like to add on or just tweak more?
I think as what Gael said, sorry for mispronouncing your name, but I think more precise on like the plastic detection, because there might be like same colored plastics as the ocean. So like our testing could, like based on that, our code would not work as well as like two different colors. So I think more precision on that value, color values, and detecting that would be best.
Okay.
Great. Thank you, TurtleBox, and congratulations on completing the Build a CubeSat challenge. Our last team up is GSSM Eagles.
Okay, so start for the GSSM Eagles project prediction. I'm Stephen Ithnars, senior.
I am Ava Perkins, and I'm also a senior.
I'm Ivan Chen, I'm a junior.
I'm Om Patel, and I'm a junior.
I'm John Jones, and I'm a junior.
So we want to give you a big overview of our CubeSat itself. So we try to go with the more minimalistic idea design. So we kept everything fit inside one complete box in order to make it stick. And in order to do this, we had to model everything in CAD, and we mainly used Tinkercad and Revly. Tinkercad we used to like put everything together, make sure it all fits, make sure all of the dimensions are correct. And we had Revly as a way for us to like view our model in 360. And it allowed us, our teammates to look at it, put a comment, say, this needs to be fixed, this needs to be put in a different place. And that allowed us to come up with our current design. And in order to fix the materials problems that we had, the lining up and everything, we drilled holes into the acrylic to meet the design that we put on Tinkercad. And we set it up in a way so that the solar panel would always be looking towards the sun and the camera would always be aligned to the Earth. So that way, when it's in space, it would always be in orbit looking at the correct way. And currently, we have the CubeSat taking a picture and sending it to our ground station via Bluetooth.
So overall, how this addresses our mission is the overall mission was to design and build a remote sensor that can detect macroplastics in the ocean from a space orbit. So as was previously stated, our design is fairly simple and minimalistic. So that everything is fitting into one CubeSat cube for ease of use and building. It's very simple to recreate and design. Our design is also durable to survive space launch and orbit, which was tested with a drop test. Afterwards, everything was working fine and there was minimal damage. Our software was also successful in detecting plastics and taking a photo and transmitting it via Bluetooth to our ground station.
So for our testing system, the image on the top right, that was what we used to test our system. So this was used to simulate the initial launch of the CubeSat from the satellite. So actually the CubeSat was able to take a relatively clear photo, but the edges were still a little blurry. From our tests, the code did work. The CubeSat was able to take a photo from the change in acceleration, and then upload that photo to our ground station. But our current code uses a change in acceleration to take the photo, but in space, the acceleration to gravity is always constant. So we would need to either change the trigger for the photo to time-based one, an angle-based one, or an acceleration-based. And then we chose to offload the processing of the image to the ground station instead of the CubeSat.
Great. So the main vectors to our design up to light, that will be pretty much our communications and our power systems. So Bluetooth, which that's going to work, right? Yes, our Bluetooth encryption system worked, which is great. Though even Bluetooth can't operate well over hundreds of kilometers between temperatures and two. So what we need is we need better antennas, something like a VHF or UHF antenna would do the trick. Now to operate that high power antenna, you need a lot of power, which means not just electric power supply. You need better ways of gathering power. You need specialized solar panels to that would drive the wattage to be able to power your spacecraft, not just like 3 seconds, but at least for several more cycles before it charges and then starts again. Another thing that's going to take a lot of power is Because again, the Pi camera itself, it's fine again, but it's okay for like close-up images. But over a long, it's very wide field camera, so it'll be hard for it to detect plastics over to detect small plastics for very long. So and also it's not suitable for operating at nighttime because it doesn't have any IR capabilities. So again, we need a better camera that could use IR vision to see and and take objects in both daytime and nighttime. And lastly, we'd have to integrate better materials. So that's like the aluminum could work, but maybe not so much acrylic, which can be a bit fragile. Because materials that can perhaps be able to shield the CubeSat from both from like the outside radiation and perhaps try to prevent some SEU from the code to also thermal insulation as well to keep temperatures inside regulated in a way.
So these are some of the challenges we had. So our CubeSat supplies did arrive slightly late, so it compensate for the decrease in time. There were machining mistakes in the material, which we fixed by drilling the holes in the acrylic to make the CubeSat that we have currently. Throughout the course, we were unsure of how to proceed at certain points. We knew the basic ideas and the basic plans that we had to meet, but because of our schedules and because we all have different class times and different sets of homework and different outside activities, we had difficulty managing and aligning our schedules so that we could effectively work on the CubeSat.
Okay, so lessons learned. I would say to communicate with our parts better. I feel like a lot of times we would work on different sections, whether it was subsystems, hardware, software, coding, or anything. I would say we would have to come together pretty much frequently or like fluently in order to like understand what each of us is doing and like be on one page. Another one would be brainstorming. Our DS with limited assistance. So, you know, this is a challenge, and oftentimes we try like get frustrated, like going to the courts and stuff. And I would say like we have to remember as a team that, you know, we have to persevere and like, you know, have freedom to be engineers and designers. Another one will be to utilize a CubeSat purpose to achieve the mission given. So basically like what we learned and like how could we better improve our CubeSat for the near future and future projects. And also utilize GitHub more efficiently and more often. So we didn't really use GitHub too much, but like I would say for future reference, we would use it more to be I guess more efficient with our coding and better communication as a team.
Thank you. I'm sorry, we can't hear you.
You're muted, Rebecca.
Sorry, I thought I had pressed unmute. Thank you, GSSM Eagles, and congratulations on completing the Build a CubeSat challenge. Once again, open it up to judges for questions.
Hello, so great job, especially with using the rod to essentially create an orbit. So how did you think of that?
So basically we wanted a way to actively simulate our CubeSat in space, because if we just held it and moved it to take a photo, it wouldn't necessarily be representative of how it would actually function in space. So we wanted a testing system in which the CubeSat would always be in movement for a certain amount of time throughout the process of taking the photo, so we could optimize and see how blurry the photo would be and how clear, and the different changes that we had to make to optimize the photo quality.
So I would like to add on that our model more specifically modeled the space of the launch of the CubeSat, since there was a factor of acceleration in our design. Even though that's not directly how an orbit would work, as was previously mentioned, then orbit, we'd have a constant acceleration. So we wanted to model it when it was moving to use that threshold of acceleration that we added into our code, and also again to see how the movement might affect the pictures.
In the future, we would probably also use the exact same system, have it more level to decrease the amount of acceleration, and test, like I said earlier, velocity, time, or change in angle for the taking of the photo.
Great.
Great work, GSSM Eagles. Just one question for you all. What was the favorite part of the project?
Well, personally for me, I really enjoyed the whole like modeling and CAD aspect of it because that's something I'm like interested in, and I did it in like other activities such as robotics. So I just found it like really interesting to see how we could like put something together in a way for everything to fit. And there's a lot of like problem solving stuff that went on. Like we had the battery previously like vertical to the CubeSat, but then we had to make it horizontal just to fit. And it's really like I don't know, relieving to just say like I made this happen and I got the whole like model to work.
I'd say for me, it was the building of the CubeSat and also the coding of our program. Seeing everything come together and effectively work was very satisfying to it.
My favorite part was, I think, the course itself more so, learning about these different aspects of how things work and how they're used and how we can apply the things that we are reading about to make this CubeSat and essentially do what was presented to us.
Glad you all enjoyed it. Thanks.
Thank you, GSSM Eagles, and all of the teams that have participated in the Build a CubeSat challenge this winter and spring. I hope that you learned a lot and that you're inspired to continue in engineering. You did a great job today, so the judges have a lot to think about. But before we get to awards, we want to share some of the other great work that you've done for this challenge. So please enjoy this highlight reel of your tech demo videos.
This is our mission demo video.
Now we will plug it in and restart it and watch the transmission to the downlink, or to the ground station. Okay, CubeSat is plugged in. Its processes will be displayed on this monitor while we wait for it to boot up. CubeSat is currently booting up. While this happens, we will talk to you about our test or demo space. So we have this blue floor with these anomalies to simplify waves and changes in depth and other things. And then we have 3 different sizes of plastic that we're going to test our program on, as well as just the floor itself to see if it can correctly identify plastic from a height of 60 centimeters off the ground. And that will represent some amount of stuff. So now the CubeSat is currently up, and now we are going to run the main system process on here. It's stored in a file called fulldesign.py, and it's a Python photo or Python file that can identify plastic, check rotation angle, and calibrate the CubeSat. So now, it's going to calibrate the CubeSat. So CubeSat is being started up. We're going to calibrate it in this position. So it's going to be focused at the ground the whole time, and the RBY trigger has activated. We're going to be holding it at 50 centimeters off the ground for our example demo. And okay, so now it's going to be checking the angle, and the RBY trigger has activated on the calibration on the regular ground, and there should not be plastic identified in this one. No plastic was detected. Let's add some plastic, and let's see if our program can detect it. So our IMU does not have a very good job identifying yaw, so this might take a little longer than expected, but it does ensure that our rotation system is working. Okay, so as you can see, the angle is being pumped out, and once it gets within the threshold, it will take a photo. Like a little more that way. Oh, and the trigger has activated, and it should identify plastic in this one. And the photo is in 2 downlink, and it'll tell us the path in a second. And it has successfully identified plastic.
Hello, we are Team TurtleBox, and the members are Jonathan Lee, Joseph Lee, Teddy Chun, Hee-sung Yang, and Chunhyuk Park. I will first demonstrate the manual mode. So first, I will run the server code from the ground station, which is the server, and I will also run the client code from the CubeSat. After they connect to each other, the window will show up in the ground station that shows the auto and manual mode. As you click Take Picture button, the CubeSat will take the picture and send it to the ground station. After receiving the file, the taken photo will show up in the window. I'll click on the color detection button next. As I click on the color detection button, the CubeSat will detect the plastic by color and send it to the ground station. This detected photo will also show up in the window. Lastly, as I click on the object detection button, the CubeSat will detect the plastic by its edge and also send it to the ground station, which will eventually show up in the window. I will now demonstrate the auto mode. When I hit run button of the auto mode, it basically runs all the functions, takes pictures, color detection, object detection, and shows all these pictures in the window. When I close the code for the server, the CubeSat prints that connection closed, and it disconnects from the server.
We went through the same process with a water bottle. Here's our water bottle, and I'm going to put it on the ocean. We ran the code from both devices, and I'm going to take a picture, and the CubeSat will take a picture and send it to the ground station. The ground station had received the picture from the CubeSat. We are not going to run the color detection because the water bottle is transparent and it is very hard to detect the water bottle by its color. The CubeSat had detected the water bottle correctly. We were successful in detecting a plastic cup and a spoon by its color and edge.
I hope that our commitment to this project will help people build a better place in the future.
Hello, my name is Julian Halpern Smith from Team LEOnidas.
Hi, my name is Krigor Chikin.
Hi, I'm Peter Becker.
Hello, my name is Nari.
Hi, I'm Declan McKinley.
The way that we have it structured is that we need to clear the file every time we run it so that it all works. Yep. And then, so then what we want to do, go into here. So now it's a little difficult. One second. Let me just position that there so that way I think that worked. So let's see. I think I ran it a few times, but as you can see here, we have all the data values that are coming in, and it takes a lot of time to analyze this, but from what I'm looking at right now, we might need to change our threshold settings, but as you can see here, the code is working. and the hardware is also working. So each one of these is a pixel. Each one of these is a pixel that has been flagged for deviating too far from the designated RGB profile. So in terms of integration and testing, we're going to be just doing this over and over again, adjusting the threshold, adjusting the quote-unquote default value for an RGB profile. And yeah, this takes a while to load, and that's another thing we need to address. But this is the way that the satellite will work. So as you can see here, I waited a little bit. The values have finally loaded, and it's flagged just under 500,000 pixels, which seems like it might be a bit too low, which means, again, we need to update our threshold settings. But as you can see, this is how the pixels would be flagged.
Hi, I'm Marvi.
Hey, y'all.
Hi, I'm Sam. Hi, I'm John.
Hi, I'm Eddie.
Hi, I'm Christian. I'm Stefan. We are Astra Navis, and we'd love to present to you our tech demo.
Let's go.
My name is Ivan Chen. I'm part of the GSSM Eagles CubeSat team. I'm here to talk about startup and our code. So on startup, after we put on the CubeSat, we SSH into the CubeSat itself, and we run the physical code itself. What the code does is that after the CubeSat reaches a certain acceleration on any axis, the CubeSat then takes a photo, and then after that, the photo is then transmitted through Bluetooth to our base station. So currently we have it so that the code only takes one photo and then sends that photo to the base station. But in the future, we plan to have the CubeSat take a series of photos and then send all those photos as soon as it detects a connection with the base station.
Hello, I'm Stephen Ismaris with the GSSM CubeSat team, and today I'll talk about how the IMU relates to the taking pictures on a CubeSat. So the IMU it measures the inertial motion of CubeSat in 3 axes, mainly the pitch, yaw, and roll axes, which are kind of demonstrated on this 2D diagram here. Now on my right, if it's there or left, you'll see video of a CubeSat rotating these axes and the IMU sending data to our ground station in real time. The IMU being able to record this data as to how much the CubeSat rotates in certain axes is how the IMU measures acceleration, and therefore enables the CubeSat to take a picture at a certain acceleration threshold. Thank you.
GSSM Eagles CubeSat team. So the entire mission of our project was to design a CubeSat which, when orbiting around the Earth, could detect plastics in the ocean using solar panels and solar energy. In the demonstration you were just shown, we showed 2 different setups which could illustrate 2 different possible orbits that our CubeSat could go through in space. As it orbits and accelerates on any axes, it will reach a certain threshold, as demonstrated with it sliding down the pipes. It will then trigger the code to take a picture of any plastics in the ocean it may detect, and then send them to our ground station. Now, obviously in the demonstration, our CubeSat did stop, which will not be realistic, but for practical purposes, I'm just able to show that it will accelerate and continue. We hope to have it can do a continuous orbit around the Earth, and instead of taking a singular picture and then transmitting it through Bluetooth to our ground station, it will take a series of pictures and then transmit all of those at once it reaches the connection of the Bluetooth again.
Hello, everyone. My name is Gael Gatera, and I'm the Outreach Project Manager for the Aerospace SIG at NSBE. So basically, I'm the one who worked tirelessly to throw this challenge together, so you can blame me for your pain. So I would like to finalize with giving out the awards. So first award is the best up and coming team. So this team gets the award for being basically the young guns of the challenge. So this award goes to LEOnidas.
Thank you very much.
You're welcome. All right, so the second award is the Innovation Award. And so this team gets the award due to their very creative and innovative test setup. So this award goes to GSSM Eagles.
Thank you very much.
All right, so the next set of awards are basically the top 3 teams of the challenge. And so coming in at third with 114 points is Astra Navis.
Thank you very much.
Thank you, everyone.
Good job. So the next 2 teams were really, really close, but there has to be a winner in many challenges. And so with 110 26 points. The second place team is Evanston Space or Bust Wildkits. All right, well, there's only one team left, and that is the winner of this challenge. So congratulations to Team TurtleBox with 127 and 34 points.
Thank you so much.
Thank you. Thank you. Thank you very much.
Thank you very much.
Problem. All right, so it has been a pleasure to both being a coordinator and a technical mentor and a judge for this challenge. So we hope to have this again next year. So congratulations to all the teams that participated. All of you are very, very smart students. Some of you having, AP classes and everything and taking basically almost college level coursework. And yeah, so congratulations once again.
Congratulations again to all of the teams, and thank you to everyone who participated from the NSBE organizers, Gael included, but also everyone else from NSBE who helped organize this, Sarah as well for judging, and all of our mentors, all of the instructors who were involved in this challenge, Dr. Colin Ward, Kerri, Cahoy. We couldn't have done it without everybody. So thank you very, very much. This has been a real pleasure to get to work with all of you students. And I know that you're going to go on from this program to do really, really great things. So once again, congratulations. To close out the day, I'd like to introduce our director, Bob Shin, for a final farewell.
Oh, thank you, Rebecca. I guess I didn't realize. Oh, okay. You have a video playing. That's
Congratulations.
great.
You are all cool-looking people ballers today. Stay safe and stay in touch.